What will happen when the sun dies? And how long will it be before the fuel runs out? What is the difference between a red giant and a white dwarf? And where can we see a red giant? And how exactly do these stars compare in size? I'm Dr. Nicholas Mee. Welcome to the Cosmic Mystery Tour. When the hydrogen nuclear fuel runs out, the sun will turn into a huge red giant star. In a star like the sun, the temperature in the core is about 15 million degrees, which is sufficient for hydrogen nuclear fusion reactions which convert hydrogen into helium. And the energy that this generates balances the tendency of the star to collapse under gravity. Now, a star like the sun can maintain this balanced state for about 10 billion years in total, and currently the sun is almost halfway through this 10 billion year time span. So in about 5 billion years time, the hydrogen fuel in the core will have completely been converted into helium, so there will be no more hydrogen fuel for the nuclear fusion reactions. These fusion reactions will then cease and the core will contract, which will raise its temperature enormously, and this will produce radiation that inflates the outer layers of the sun until it becomes a huge bloated red giant star. When the sun bloats into a huge red giant star, billions of years from now, its outer layers will swallow the inner planets, Mercury, Venus and the Earth. Fortunately, we won't be around to see this. There are, however, examples of red giant stars that we can see. So where can we see a red giant star? This image shows a famous constellation, Orion the Hunter. Its shoulder is the orangey-red star Betelgeuse, which is a red giant. Betelgeuse is a huge star, but it has a mass that's several times the mass of the Sun, and its fate will be different to that of the Sun, so we will leave Betelgeuse for another video. But behind the trees we can see another constellation. The V-shaped collection of stars is the forehead of Taurus the Bull, and we can see the angry red eye of the bull, the orangey-red star Aldebaran. Now, Aldebaran is slightly more massive than the Sun, just 16% more massive, but Aldebaran has already used up the hydrogen nuclear fuel in its core and has swelled up into a huge red giant about 40 million miles or 60 million kilometres in diameter. So it's 40 times the diameter of the Sun, and this makes it much brighter than the Sun. So at a distance of 65 light years, it's still one of the brightest stars in the sky, about 500 times as bright as the Sun. If the Sun was at this distance, we wouldn't even be able to see it with the naked eye. We can see here just how big Aldebaran is. Jupiter is over 10 times the diameter of the Earth. The Sun is 10 times the diameter of Jupiter. But Aldebaran is about 40 times the diameter of the Sun. And most models predict that eventually the Sun will be even bigger than Aldebaran is now. Deep within a red giant star, the core continues to contract until temperatures reach about 100 million degrees. And at this temperature we move from the hydrogen nuclear burning phase to the helium nuclear burning phase. At these temperatures, the helium nuclei are smashed together with such ferocity that helium nuclei fuse to form carbon nuclei and oxygen nuclei. So gradually the core of the star is converted from helium into carbon and oxygen. Now these nuclear fusion reactions don't generate as much energy as in the hydrogen nuclear burning phase, so this phase of the star's life is comparatively shorter. In a star like the Sun, this phase might last hundreds of millions of years, but in a much more massive star, it can be much shorter than that. Eventually, all the helium in the core is converted into carbon and oxygen, and we reach another crisis point. The nuclear fusion reactions cease, and the core contracts and the temperature rises. In a really massive star such as Betelgeuse, this will lead to new rounds of nuclear fusion processes. But we will come to these in the next video. For now, we will continue with the fate of the Sun. In a star like the Sun, the carbon-oxygen core contracts and the temperature rises, and this produces a blast of radiation that sends the already distended envelope of the red giant star off into space. And the blazing hot core of the star emerges shining like a crazy diamond in the night sky. The radiation illuminates and excites the expanding gas cloud to form a planetary nebula, one of the most beautiful sights in the night sky, that's often been compared to a cosmic butterfly. These nebulae have nothing to do with planets. So why are they called planetary nebulae? Well, they do look a bit similar through a low-powered telescope. Even through a telescope, stars look point-like, but these nebulae have gas that's expanded so much into space that they look like a smudgy patch, which could be confused with the face of a planet. And after discovering the planet Uranus in 1781, William Herschel thought that they looked so similar that he called them planetary nebulae. There are many examples that can be seen in the night sky, even with a modest telescope, and some incredible, beautiful images have been produced by larger telescopes such as the Hubble Space Telescope. Often the white dwarf itself can be seen shining away, surrounded by the nebula. But planetary nebulae don't last for very long by astronomical standards. After a few tens of thousands of years, the gas disperses into space and the show is over. Although white dwarf stars are incredibly hot, they are also very faint. And this is because they are so small compared to ordinary stars. A star-sized amount of material has been compressed into a planet-sized volume, and this means that they are about 1 million times as dense as water. So if we scooped out a teaspoonful of material from a white dwarf and transported it back to Earth, it would weigh over 10 tons. Even with sophisticated computer models, it's difficult to determine how much of the original star ends up compressed into the white dwarf and how much is eventually lost into space as the gas of the planetary nebula. For a star like the Sun, it might be a 50-50 split. The temperature of the white dwarf is over 100 million degrees when it first forms, but even this is not sufficient to trigger a new round of nuclear fusion reactions. So the heat of the white dwarf is eventually radiated into space over the course of billions of years. It is now just a white, hot, dying ember. The nearest white dwarf to us is Sirius B. It's about 8.5 light years away, and it's the companion of the star Sirius, which is the brightest star in the night sky. Sirius is in the constellation Canis Major, the Big Dog, so it's also known as the Dog Star, and for this reason Sirius B has been nicknamed the Pup. We can see here the great differences in size of the red giant Aldebaran, the Sun, and a white dwarf Sirius B. Despite these great differences in size, each of these three stars has about the same mass, and this is about 1,000 times the mass of Jupiter, or 300,000 times the mass of the Earth. Unfortunately, because Sirius B is so small, it is far too faint to see with the naked eye. It is even notoriously difficult to spot with a modest-sized telescope. But there is more about this curious star and how it was discovered, along with many of the other mysteries of the cosmos, in my new book, The Cosmic Mystery Tour. In billions of years' time, all that will remain of the Sun is a white dwarf star similar to Sirius B.